Hello, everyone. My name is Amanda Haller with Audio Precision, an Axiometric Solutions brand, and today we are featuring audio testing in smart devices. Today we have Eric Schultheis as our presenter from Axiometric Solutions. Before we begin, I wanted to cover a few housekeeping items. A copy of today's slide deck is available through the Handouts section on your screen, along with various related handouts. If you have any questions during the webinar, you can submit them through the questions section on your screen, as all audience participants will be muted during the presentation. We will try to answer these questions during the webcast, but if we run out of time or if a longer explanation is required, you will be followed up with after the webinar via email. Without further ado, I would like to pass it over to Eric to get us started.
Thank you, Amanda. Hello, and welcome to the Audio Precision and GRASS Sound and Vibration Smart Device Audio Test webinar. My name is Eric Schultheis, and I'll be presenting the following slides to you today. Here's what we'll cover in today's webinar. I'll make a short introduction to our company's products and services. I'll talk about open and closed loop audio measurements and how these apply to testing smart devices. We'll look at basic audio tests, some of the measurements you'll need to make. I'll discuss procedures for testing playback-only devices as well as recording-only devices. Next, we'll look at test system components you may want to consider. And I'll leave some time for questions and answers at the end of the presentation. I've been at Audio Precision for 20 years, where I work in the global tech support team. I support Audio Precision and GRASS products alongside my colleagues here in Beaverton, London, and Copenhagen. When I'm not supporting our customers and products, I enjoy playing guitar, practicing yoga, and outdoor activities like cycling, hiking, and kayaking. If you have questions or need assistance with the topic we're covering here today or other issues, please reach out to us by email at techsupport@ap.com or support@grassacoustics.com. It really doesn't matter which address you use. They will both be seen by our support team. Audio Precision was founded in 1984 by 4 engineers, Bruce Hofer, Rich Cabot, Bob Metzler, and Bob Wright, who met each other while working at Tektronix. For almost 40 years, we've been the recognized leader in audio test and measurement solutions. We design, manufacture, and service our products here in Beaverton, Oregon, USA. While many customers are still using the original System 1, we have progressed over the years, adding performance, features, and capability while streamlining the user experience. GRASS Sound and Vibration was founded in 1994 by Gunnar Rasmussen. GRASS is recognized in the industry for innovation, groundbreaking designs, and a dedication to customized customer solutions. All GRASS products are made in Holte, Denmark. GRASS products are available for a wide range of electroacoustic testing applications. Our products include measurement microphones, ear simulators, head and torso simulators, test fixtures, and calibration solutions. IMC Test and Measurement, located in Berlin, is the third company under the Axiometric Solutions name. Together, as Axiometrics Solutions, we provide test and measurement solutions for many markets, applications, and customers around the world. Now, we'll look at a closed-loop audio test. As the name implies, the loop or signal path is closed. That is to say, the audio stimulus generator, the device under test, or DUT, and the audio signal analyzer are all working together at the same time in harmony. The generator creates a pure stimulus signal, usually, but not always, sine waves, sending the signal to the DUT's input, while the DUT's output feeds the signal back to the audio analyzer, which will compare the received signal to the original generated signal, then calculate and post the results. Here are some examples of devices which are tested in a closed loop configuration. Basically, any device that passes an audio signal from its input to its output in real time. When making an open loop audio measurement, the signal path or loop is open, meaning the generator and analyzer are not working together in concert. They are separated from each other. This type of signal path configuration is necessary when the device under test is not able to pass the stimulus signal through its input to its output in real time. In many cases, the DUT may not have physical inputs at all. The input to this type of device could be a file in the cloud, on a network, on an SD card or a disk, or even an analog recording on vinyl. Some devices do have inputs. However, the input may be difficult or impractical to access. So open loop testing is the preferred technique. DUTs which require open loop testing fall into three main categories: playback-only devices, reproduction devices, and broadcast or transmitted devices. To test playback-only devices, the stimulus signal must be placed onto and then played from the device or streamed into the device and played from its output into the audio analyzer. This is a two-step process where step one is creating the stimulus signal and moving it to the device or to the network, and step two is playing the stimulus signal from the device or streaming it to the device while analyzing its output. Here we see some examples of reproduce devices. These can include audio and video recording devices, PCs, smartphones, and tablets. This category of DUT has two signal paths, record and reproduce, each requiring an open loop configuration and a two-step process for testing. To test the record signal path, we first play the stimulus signal from the APX generator into the DUT while recording it onto the DUT's file format and media. Next, we move the recorded file to the test system's host PC and use file analysis in APX 500 software to analyze the recorded file. To test the reproduce signal path, we follow the same step one as described above, and then play back the recorded file from the DUT to the analyzer to be analyzed in real time. Here is the procedure outline for an open loop test of a playback-only device. Step 1 is to configure the generator. Step 2, we generate the stimulus wave file. Step 3, we encode the wave file for the DUT or the network if necessary. Step 4, we then upload the stimulus file to the DUT or to the network to be streamed to the DUT. Step 5, we start the analysis acquisition. Step 6 is to play or stream the stimulus file from or through the DUT to the analyzer. And then finally, step 7, the analyzer acquires the signal and posts the results. Here we see the outline for a record device in greater detail. The procedure is as follows. Configure the generator for the desired stimulus signal. Configure the record device and start recording. Generate the signal from the APX analyzer. Then stop the recording on the DUT once the signal has been recorded. Next, we transfer the recorded file from the DUT to the host PC. Then we decode the file if required, and finally analyze the file with APX500 software in file analysis mode. Of course, most smart audio devices have speakers and microphones, which add to the complexity a bit. An electroacoustic open loop measurement might add step 2 above, equalizing the speaker or the mouth simulator to produce a flat response or a leveled acoustic output. We're also adding step 8, windowing out reflections from the impulse if a chirp measurement is used without an anechoic chamber. Smart speakers have two audio signal paths, the voice command path and the streaming path. The voice command path is a record-only path, and the streaming path is a playback-only path. Now that we've seen smart device signal paths from the outside of the device, let's have a look inside the smart device. This block diagram shows various circuits or components within the device which can each be tested for quality. Most of these components can be isolated and tested in closed loop configurations, although optional digital input-output modules may be required in the APX analyzer to make the necessary connections. We'll see more on that in a few minutes. Many audio measurements are made using sine waves to stimulate the device under test. We generate a pure sine wave, which is played or transferred to the DUT. The DUT will play or pass the sine wave back to the analyzer, where it's analyzed for any changes from the original signal. Frequency response is probably the most telling measurement result. We can use stepped frequency sweep, continuous sweep, multitone, and transfer function measurement techniques in closed loop or open loop signal path configurations to show us the response as well as other results. The stepped frequency sweep measurement uses a sine wave stimulus signal that's moved across a range of frequencies in a series of steps or points. Stepped frequency sweep provides a sweep table editor where you can set step points and durations, as well as create a wave file of the stimulus signal for open loop use. Distortion, phase, and synad results are also provided in this classic measurement technique. Continuous sweep is a chirp-based measurement using a brief Farina log-swept sine or chirp stimulus that moves continuously across a specified range of frequencies. The DUT output is acquired by the analyzer and is mathematically deconvolved to produce a number of results. The continuous sweep measurement has a save generator file feature for open loop testing, and like the stepped sweep, provides response and additional results. The major difference between these two measurements is the speed of operation. Stepped sweeps can run for 30 seconds or more, while continuous sweeps are generally completed in less than 1 second. While stepped sweep measurements are historically standardized, the log swept sine or chirp measurement has some significant benefits. It's much faster. It provides quasi-anechoic electroacoustic measurements, plus rub and buzz results. In a closed loop test, the generator and the analyzer work together, informing each other of starting a measurement, moving to the next measurement step, and when the measurement is completed. When making open loop sweep measurements, we use a pilot tone just before the stimulus signal to trigger the start of the measurement. The pilot tone is usually a 1 kilohertz signal. Here's a view of the chirp stimulus. You can see the pilot tone on the left and the chirp signal on the right. Here we see the stimulus waveform for a 350 milliseconds long sweep from 50 hertz to 8 kilohertz, with a pilot tone and the wake word inserted before the chirp signal. The analyzer triggers on the pilot tone and uses the pilot tone frequency to correct for any slight sample clock difference between the DUT and the analyzer. In this case, the wake word and the pilot tone are not included in the analysis of the frequency response. The APX 500 acoustic response measurement is a chirp-based measurement with time windowing to gate or window out acoustic reflections from your results. If you don't have an anechoic chamber for making electroacoustic measurements, this feature will help. Acoustic response measurements can be made in closed loop or in open loop configurations. The APX 500 multi-tone measurement, as the name implies, uses multiple sine waves together. This signal is more like program material or music. Smart audio devices employ codecs, which reduce audio data rates for streaming. Some of these codecs tend to mask sine wave signals, and as such, we must use a measurement requiring a stimulus signal other than sine waves. In this spectrum display, we can see each of the separate tones in the multitone signal. This example uses 31 tones with 1/3 octave spacing. The multitone signal definition enables the analyzer to trigger on the multitone signal itself. The multitone measurement does not require a pilot tone to trigger in open loop configurations. Transfer function provides the difference between two audio signals by comparing the complex spectra of the two signals. This feature, which uses FFT analysis on the two signals, is also called dual FFT. One of the most powerful aspects of this measurement technique is that the stimulus signal can be tailored to suit the device under test or the testing environment. As long as the signal used is broadband with sufficient energy across the spectrum of interest. Transfer function is an excellent choice for testing the input path of a smart speaker because a speech or speech-like signal can be used as the stimulus, virtually ensuring that the signal will be acquired and processed unaltered by any noise-canceling algorithms or codecs. Transfer function analysis can be used for the output path of a smart speaker also, using music or noise as a stimulus. To avoid reflections, an anechoic chamber should be used when making electroacoustic measurements, unless you're using the acoustic response measurement with its time windowing to gate out the reflections. Next, we'll look at the various components and options for the test system. The APX 517B is an excellent match for testing many smart audio devices, as it's set up out of the box for electroacoustic measurements. It has a 35-watt power amplifier, a stereo headphone amplifier, 2 microphone inputs with CCP and phantom power options, and a single slot for an optional digital I/O module. It's pictured here with the optional Bluetooth digital I/O. These are the optional digital I/O modules available for APX analyzers. Up to 4 option modules can be fit into APX 52X, APX 58X, and APX 555 analyzers. One option module can be fit into the APX 517. One or more of these digital I/O modules may be necessary to test various components, circuits, and signal paths within a smart audio device. The GRASS 46AE half-inch CCP free field measurement microphone is a great workhorse reference mic for making acoustic measurements on smart speakers. It will interface directly with the APX 517 or any other APX analyzer using one of the 12 series power supplies, or using the APX 1701 transducer interface. The 46AE conforms with IEC standards. The EQ40PM miniature production line microphone is the first microphone to incorporate EQset technology. This removes all of the traditional hassle associated with installing, setting up, and replacing microphones in a production line setting. EQset microphones all have flat response curves and fixed sensitivity. Sensitivity variation between individual microphones varies less than 0.2 dB from nominal sensitivity. The flat frequency response, less than 0.5 dB up to 10 kilohertz, another huge improvement over traditional production line microphones, plus or minus 3 dB across the full frequency range. The 44AB passive mouth simulator connects directly to the APX517. This is used for testing microphones in smart speakers and speaking wake and command words to the DUT. Jigs are included for calibration according to CCITT-P.51 and IEEE 269.661 standards. The model 44AA is similar, but also includes an internal amplifier with 10 dB of gain. The Grass AL0030 production line acoustic test chamber will provide approximately 25 dB of separation for making electroacoustic measurements on a noisy production line floor setting. It is built from medium density fiberboard lined with acoustic dampening material. A large opening at the back of the chamber allows easy access to the chamber for configuring the test setup. The chamber has shock and vibration absorbing feet that prevent vibration from the outside from influencing measurement results. On the software side, you'll need APX 500 measurement software, which comes with all APX analyzers as standard. APX 500 measurement software is the most advanced audio measurement interface available. Complex procedures that include user prompts, limits, and calls to external applications can be created directly in the user interface. This software controls the APX hardware in manual and automated applications. APX 500 can also be automated via the APX API using Visual Basic.NET, C#, MATLAB, LabVIEW, and Python. While you can use APX 500 measurement software to generate and save stimulus waveforms, this APX 500 waveform generator utility also does the same for mini stimulus signals. The utility is a small standalone application and it's a free download at ap.com. Another handy tool I recommend is Audacity. This DAW, or Digital Audio Workstation software, is free of charge and open source. It will run on PCs, Macs, and Linux. This is a great solution for building and editing stimulus wave files. Here are some additional sources of information pertaining to smart device audio testing, which may be helpful. You can download these documents from the handouts area here in the webinar. You'll also find these and additional resources on the Audio Precision and GRASS websites. This brings us to the end of this presentation. I would like to thank all of you for attending and remind you of the next webinar in this series on June 28th, when the topic will be headphone testing. I would also like to thank Amanda for all her help putting this webinar series together. We still have some time for questions, so we'll open it up for that now. Okay, we have a question here. When doing dual FFT frequency response in open loop, is a pilot tone required? The answer is no. A pilot tone is not required when using transfer function, also known as dual FFT. So the signal itself is matched back to the reference signal, and you do not need a pilot tone. How is the stimulus onset detected, and does it compensate for differences in clocks? Yes, we do have a matching algorithm which does have frequency error correction, and the files are matched to each other, so it will work without a pilot tone. Another question we have: why do I always hear a clicking sound from inside the APX analyzer? So the clicking sound that you're hearing are the input ranging relays. So if a system is sitting open on a production floor with a microphone connected to it as the input, it is ranging up and down as the microphone is picking up transient sounds and audio around the room. And you can fix this by locking the range using the Advanced Settings button for the specific measurement that you're using. The range will always range up to protect the analyzer inputs, even though the range is locked or fixed. And that's just protecting the instrument from overload at the input. I have another question here. Does the pilot tone need to be the same level as the stimulus signal? No, it does not. Generally, you'd like it to be about the same level, but it does not have to be the same level. It should be within a range. You wouldn't want, say, 25 or 30 dB difference between the pilot tone and the stimulus. Let's see, we have one more question here. Can the 517B option modules be changed while the analyzer is working on a production line? Unfortunately, no. To change a option module in any of our analyzers, it has to come to a service center where the work would be performed, and then the instrument must be calibrated after the service is done. After the module swap is done, the instrument must be calibrated. Let's see. Question here. I guess this is a follow-up question on a previous question. Does this estimate of clock difference update continuously while the file is being played? No, it is not continuous. So that looks like, okay, so we have one other follow-up question. So if the DUT clock suddenly changes for some reason mid-stimulus playback, can this be accounted for? No, if the clock changes midway, then it would lead to some problems with the result. Your results would show that there would be drift in the frequency. So it looks like that's all of the questions that we have. I would like to thank all of you for attending today. And I would like to also thank Amanda for her help today. And I'm going to turn it back over to her now.
Thanks, Eric, and thank you for that excellent presentation. We would like to thank our audience for your participation today and the excellent questions that you sent in. If you are still sending in questions, we will get back to you via email. An on-demand version of today's presentation will be sent to the email you registered with. Also, be sure to register for our upcoming webinar testing of headphones and headsets on June 28th. That will be included in the follow-up email. If you have any questions after today, please feel free to reach out and we will get back to you as soon as possible. We hope you have a great rest of your day and we look forward to next time.